Thank you very much for coming. My name is Joseph Gelfand. I'm an assistant professor of physics here at NYU Abu Dhabi, and it's truly an honor and privilege to be able to introduce Krista Cugliotto. Since she got her PhD from the Technical University of Munich, she's one of the foremost high-energy astrophysicists today, especially in the field of transient phenomena. She discovered magnetars, these neutron stars with ridiculously strong magnetic fields you'll be hearing about. She's the one who established that short gamma ray bursts and long gamma ray bursts are quite different. And for her work, she's been awarded, let me see, the Descartes Prize, the Rossi Prize, the Heinemann Prize, the NASA Exceptional Service Medal, the Greek Government Order of the Phoenix Commander Class Medal. She has, in addition to the PhD from Technical University, you have 2 honorary degrees, one from Sussex University and the other from the University of Amsterdam. She's a fellow of the American Physical Society. She's a fellow of the American Association for the Advancement of Science. She, in the past, was chair of the High Energy Astrophysics Division of the American Astronomical Society, the Division of Astrophysics at the American Physical Society. She just finished her term as vice president of the American Astronomical Society. So, of course, now you're president of Division D of the International Astronomical Union. After a long career at NASA Marshall Space Flight Center, she is now a professor of astrophysics at George Washington University in Washington, D.C., where she's establishing a group to study the transient phenomena she'll be talking about today. So, thank you.
Hi, good evening, good afternoon. It's a pleasure and an honor to be here. Thank very much Joseph Yossi Gelfand and the NYU Abu Dhabi Institute for the invitation. And get ready to travel across the universe with me. I am a high-energy astrophysicist, but that doesn't mean that I only care about high-energy astrophysics. What I wanted to show you right now, is that okay? Yeah, you can hear me if I use this. What I wanted to show you is the enduring quests that the scientists have been asking in astrophysics across the decades. The questions that the humanity has encountered and we're still trying to answer focus on basically 3 areas. The first one is, how does our universe work? I'm probably better off here. How does our universe work? How does the universe start and where is it going? Can we probe the origin and the destiny of our universe? This is a question that we've been trying to answer for quite a while, and I suspect we still will try for a while some. So the second question is, how did we get here? From the beginning of the universe to the galaxies, the formation, the evolution of the galaxies, the stars and the planets, how did that happen after the Big Bang that created the universe? And we are finding ourselves on the planet Earth, occupying a very tiny place in the universe. And the question is, of course, are we alone? We need to discover and study other planets around other stars and explore whether they can harbor life. I personally work in the first 2 areas more than the last one, but I have to say I'm equally interested in all of them. And now, going to the areas that I work on, I'm going to talk to you about what are the tools we're using in order to discover all the stars and the transients that we're looking at. Photons are the most abundant messengers in astronomy, in astrophysics. And what you probably are not familiar as in that form, but you have encountered all these wavelengths, is the electromagnetic spectrum. Photons of different energies occupy different areas in the spectrum. What you really know and probably cherish, except for colleagues in the room, is the visible part of the spectrum, which basically is what we can see with our own eyes. The rest of it is not observable from the humans, but we use different machines, different tools to observe it, and it extends from the radio wavelengths up to the gamma rays. And we now have observations in every single wavelength. However, there are other messengers that we can use to get information about the universe, which I will not expand on. And these are the cosmic rays, which are very heavy nuclei, and they are also charged. And then gravitational waves, I will touch upon this towards the end of my talk because it's very important for us. We just opened the window of gravitational waves, and neutrinos, which are small particles that are created in supernova explosions and gamma ray burst explosions, among others. The tools that we have to observe all that vary with wavelength. For instance, if we look in radio, we can have observatories on the ground, ground-based observatories, like ALMA in Chile and Arecibo in Puerto Rico, but also have space missions as well. If we go into the infrared, we have missions, and the visible, we have also the Hubble Space Telescope and also the Keck observatories, among others. I mean, there's many more, I just put the biggest ones right there. And the only place where we do not have any ground-based observatories are the wavelengths where I'm working on, the X-rays and the gamma rays. Basically, this is good for us because this means that the gamma rays and the X-rays, in particular from the sun, do not reach the surface of the Earth. In other words, we survive being baked in X-rays. And then finally, we have the gamma rays here and very high energy gamma rays, which is also being observed via secondary interactions on the ground. So going into the electromagnetic spectrum, their messengers are the photons. They're the most abundant messengers in the universe. For each photon, we collect information. What kind of information do we collect? 4 kinds, different types. One is the direction, which was the direction the photon came from. The other one is the arrival time. Exactly when did the detector record the actual arrival of the photon? Then the energy. How much energy did that photon have? And we are hoping in the X-rays and gamma rays, because we already have done this in the radio and the optical, to open yet another window, which is the polarization, polarimetry window, which basically is the measurement of the plane of oscillation of the wave of the electron when it moves through space. So basically, let's go now more closely. I'm zooming in more and more into the area I am going to focus on. And let's talk about transients. This is the night sky, and this is in the optical. So what you see here is a plethora of stars. When you have a very big explosion in the optical, that can actually be observed with naked eye. This is, for instance, the explosion of a massive star, a supernova, which was seen by Tycho in 1572. It's called now the Tycho supernova. And today, or actually not today, but 2010, 400 some years later, we see it in the ultraviolet, and it's now expanded. So we see a much more, a larger source in the sky. The transients that we will talk about are not optical transients, and I will show you why. We will talk about high energy transient phenomena in X-rays and gamma rays. Now, this is a very busy plot, but it's only qualitatively so. What I have here is a timeline of variability. And all these blobs that I plotted here indicate different phenomena and the scale where you will see them vary. For instance, magnetars, short gamma ray bursts and long gamma ray bursts, which are the 3 phenomena I am going to discuss, vary in very short time scales of the order of milliseconds, 1,000th of a second, up to seconds, thousands of seconds in many cases for the long gamma ray bursts. And the origin of the source is either a neutron star or a black hole. And in the case of magnetars, it's neutron stars. I will very briefly describe them. And in the case of gamma ray bursts, we do believe they're black holes. So when you look at very explosive transient phenomena, or variability, I should say better, in the optical, there is a huge background that you have to fight with. All these are stars in a galaxy. In fact, this is NGC 2770, which so far has recorded 3 supernovae, and we call it the supernova factory. You would see them if you looked there, but there is if you have less bright, fainter, I should say, transients, you would have a hard time to seeing them. But if you go to gamma rays, here is one of the brightest transients that I'm going to talk about. This is a gamma ray burst. And so why do we use gamma rays? Because it's very easy if you have monitors in gamma rays to see something that comes up, because there's very few of them. So you immediately will see it, and you will be able to point other telescopes and identify the origin of the phenomenon. So this is the event. This is the same part of the sky before the eruption. There was nothing there. And then about, I believe, 3 hours after was the eruption of a gamma ray. And later, there was again nothing. This event lasted several hundreds of seconds. What are gamma ray bursts? Let me take you a little bit to the particular cases, which I will bring up with serendipity. Because in science, we have either a way of following ideas, and there is another way of nature to come up with surprises. And we cherish surprises as much as ideas. So in this particular case, what we have is the 3 governments, the United States, the then Soviet Union, and the United Kingdom, signing in 1963 what they called the Nuclear Test Ban Treaty, which actually was going to prohibit, to test or monitor the fact that there were no nuclear detonations in space or in the atmosphere. So these were satellites that were actually monitoring keeping with the treaty from all over the world. At the same year, 1963, when the 3 nations signed the treaty, the United States launched the Vela satellites. These are the Vela satellites. In fact, there is 2 of them. And when they launched, they separated. So there were always 2 Vela satellites. They were in pairs to make sure that they covered both hemispheres. So basically, they launched these satellites to designed to detect nuclear explosions in space. These were built in Los Alamos National Laboratory. These were military satellites. However, on July 2nd, 1967, they detected a flash of gamma radiation, which was like nothing known before and had nothing to do, it didn't look at all like a weapon signature, like a nuclear detonation, but it did have some properties that were actually measurable and similar. So what did the Los Alamos people do? They put it aside because they thought they could identify, because of the satellites and the way of triangulate back to the detection, to the direction of the arrival of the photon, they could identify that eliminates the Earth and the Sun as a source. And they set it aside until 1967, when the scientist Ray Klebesadel, who was actually the first author on this paper, had time to analyze the data, and they identified 16 short bursts of photons, which basically were very high energy and they had no idea what they were and where they were coming from. This is the very first burst. What you see here is the time elapsed from the first photon detected until the last, and you see how many photons per second arrived at the detector. So this is what we call a light curve. How the light evolves, emitted from the source, evolves with time. As you can see, it's very primitive. It wasn't meant to detect gamma ray bursts, and you couldn't have all the detail that we have today, as I will show you. However, the field started becoming very active very soon. At the Vela time, we could get 10 to 20 per year. Right in the 80s, there were 50 and 100. And in the 1990s, there was a special mission built just to detect them. And we identified the rate 300 to 350, basically 1 gamma ray burst per year. Then the Compton Gamma Ray Observatory was deorbited. It ended its life in the ocean, in the Pacific Ocean, if I remember right. And we had the black ages, or the dark ages, I should say, of the gamma ray burst field. And basically, until 2008, when the Fermi mission was launched, especially with an instrument to detect gamma ray bursts, we went back to 300 per year. So the initial questions of the actual field was, the very first question is that for real? Is that a real phenomenon, astrophysical phenomenon? Is it man-made? Is it a fluke? We didn't know. However, if it is a real phenomenon, where does it come from? Does it come from the solar vicinity? Does it come from our galaxy, or does it come from outside the galaxy? Obviously, this has very significant consequences, because if it did come from outside the galaxy, it meant that the light had to travel huge distances, which means that at the source, at the origin, it would have to be extremely bright in order to reach us from these distances. So what are the durations of these events? What are the energetics? How much energy is released during this event? What source can make a gamma ray burst? And what are the central engines that are actually feeding the monster, feeding the gamma ray burst? So it was prime material for another great debate. The first great debate was in 1920 between Shapley and Curtis to discuss the scale of galaxies. The scale of gamma ray bursts fell right into this particular area as well. So Bogdan Paczynski and Don Lamb debated in 1995 at the 75th anniversary of the first debate. And by the way, there is 2 more that happened after that, whether are gamma ray bursts from other galaxies or are they from our own galaxy. After about an hour of debate, nobody convinced the other one, and the audience was completely confused and they wouldn't even know where to go. However, we voted at the end, and they were 50-50 more or less, with a slight preference for the extragalactic origin, which was actually confirmed when we were able to identify what we call the counterpart of the gamma ray emission in the X-rays and in the optical. What you see here is the Beposat satellite instrument, the wide field imager, the wide field camera, sorry, the WFC, basically during the event and 3 days later. There was an afterglow, there was a counterpart which lasted less than a day. And here you see the same exact, phenomenon. There was an optical transient with the William Herschel telescope and with the Isaac Newton telescope. February 28, the same day that this event went off in gamma rays, we pointed both. We saw 2 counterparts, one in X-rays, one in the optical, and 3 days later, this thing was gone. in both cases. So this transient phenomenon was associated with the gamma ray burst. So for the first time, we found something that was associated, and it wasn't from our own galaxy. Very soon after, we actually had a lot of more information, and we were able to identify the second event very close to another galaxy. So in the end, in 1997, in February and in May, these were the two discoveries that clinched it, and we now know that gamma ray bursts are coming from other galaxies. And what we did is, with the two major satellites that actually observed gamma ray bursts, we put them on the map. And this is in galactic coordinates. And forget the colors, they are actually, the color codes are related here with the intensity of the events, how bright they are, and here with the different instruments that observed them. Here is just one instrument, the burst and transient source, transient source experiment, sorry. I worked 10 years on that, I should know it better. So basically, this had 2,704 gamma ray bursts. I worked a lot on this data. And then I joined the Fermi Gamma Ray Burst Monitor and SWIFT. And basically here is the map, which was launched in 2008. This is the decade of 1990 to 2000 and 2008 onwards. And basically these two maps show that there is no preference in space from the gamma ray burst to come from everywhere in the same way. So at that time, at 1997, we knew that gamma ray bursts were extragalactic phenomena. We also knew then that they are the most luminous explosions known to occur in the universe. Luminous means intrinsic luminosity, where they explode. When they come to Earth, they lose intensity, but because sometimes we can measure their actual distance, we know how much energy was released in situ at the place of the explosion. And they're also catastrophic phenomena, which is important. When you see a gamma ray burst, you just witness the birth of a black hole. It kills the star and it creates a black hole. So, what are black holes? This is a very simple version of what black holes are. According to the theory, Einstein's theory of general relativity, black holes are points in space where the gravitational potential, the gravitational force is so strong that everything that goes near the black hole gets swallowed by the black hole, and not even light can escape the black hole. So everything that goes near the black hole, in other words, it goes beyond, closer than the event horizon, which is the imaginary surface of the black hole, the surface of no return. So how can we then observe them if there is no light escaping? Because light is the messenger that we're using. So we have to be inventive. We can observe them by orbiting the different behavior of stars around the center of a galaxy, which means if there is a black hole in the center, you see stars orbiting around something that you cannot see, you can calculate the mass and you can identify the central unobservable object as a black hole. Also, you can study them by measuring the radiation from binary systems. When there is a star orbiting a black hole, you see X-rays. And of course, you can observe them with gamma ray bursts. The different masses that we see black holes, or rather we think they exist, although we just have some evidence for this category, are stellar size in binaries and alone, and this is the gamma ray burst category. There's intermediate size, and you can find them in galaxies, so this is a binary system in particular of a black hole, and here is a ULX, an ultra luminous X-ray source, which could be associated with an intermediate mass, which is several thousands of solar masses. And then you can find supermassive black holes. Now we know that each galaxy has in its center a black hole, and so does our own galaxy. There is a black hole in the middle of the galaxy. So this is about 4 million solar masses, if my memory does not fool me. And basically, they're in the centers of every single galaxy right now. Now, if you go into the galaxies that we have associated with gamma ray bursts, you see here images with the Hubble Space Telescope of a mosaic of galaxies that black holes have been found in. And this cross here is the location of the gamma ray burst. There's a couple of things that jump up. The gamma ray bursts are located in the brightest parts. You can't see it everywhere. You can see it in the majority of them. But that means that they are concentrated. The brightest parts of galaxies are the parts where massive bright stars are actually concentrated. That means that where the massive young stars are concentrated, there is ongoing active star formation in this galaxy. So the host galaxies for gamma ray bursts are irregular in shape. They don't have the elliptical shape or the spiral shape. They're in their majority irregular. They have a small amount of metals other than hydrogen, which is the predominant element in the universe, and helium, which is 70 to 30%. And then basically there is high star formation rates in all these galaxies. So now, if you follow the gamma ray burst, here is the map of our galaxy, here's the galactic disk, and here is a gamma ray burst that actually erupted somewhere here, as you will see when I click the movie. And what I'm showing here is how this light curve evolves as the image also gets brighter until it disappears. So there's two areas. There is the burst here, and then there is the light curve. And I will play it one more time. That's how we collect the light curves, photons in time, how they arrive. And what do we do with these light curves? There isn't much we can do. We tried to classify them. We're an astronomer. We are astronomers. Astronomers classify everything, and then they sub-classify. We have categories, subcategories, and offshoots or trees coming off of sub-subcategories. In this particular case, we would need 2,704 categories to classify gamma ray bursts, because when you've seen one gamma ray burst, you've seen one gamma ray burst. So basically, they're all different, but what we can do is measure their durations, which is very interesting, because what we did is we found out that we can broadly categorize them into two types, the short ones and the long ones. And the important thing is that the short ones have also, most of their photons are in high energies. And for the long ones, most of their photons are in low energies. So there is two types of properties that keep these two categories separate from each other. I should hasten to say that there is an overlap, and basically the duration is a particular type of measuring, which I'm not going to go into details. And these are the two extremes. This is the shortest event recorded, which is about 6 milliseconds, 6,000ths of a second. And there is a feature here that's important of 200 microseconds. And then there is the longest continuous event recorded, which was about 2,000 seconds. And today we have ultra long gamma ray bursts, about 10,000 seconds long. So the durations of the phenomenon span 6 orders of magnitude, which is impressive for a single phenomenon. Now, why do we care about the durations? I should actually ask our fellow theorists, theoretical astrophysicists, which claim that each particular category is associated with a different origin of the phenomenon. The ones that are short can be produced by mergers of neutron stars. And here you see an artist's conception of how two neutron stars will merge. They just rotate around each other, and at a certain point of time, they merge into another, producing a huge explosion with two jets emanating from both sides. And basically, this is what we observe as the gamma ray burst. The beauty of this model is that it's testable because mergers produce gravitational waves. And I'll show you at the end of my talk how we're going to prove it or measure it. However, the longer gamma ray bursts are produced by another model, which is called the collapsar model. This one claims that a massive star collapses into a black hole, and in the collapse, also material is being reflected from the actual surface of the, and then basically it creates a huge jet that we observe as a gamma ray burst, and you see the ejecta as well as they expand. This is the so-called collapsar model, and it's associated with the long gamma ray burst. That one is not predicted to produce gravitational waves, to my knowledge. Regardless what creates a gamma ray burst, be it a collapsar or a merger, after the explosion, after the initial phenomenon, what happens is, as the jets go on, they start moving in different fronts. So basically, this shell collided with another shell and created an internal shock wave, and then the very first shell collided with the material that was emitted from the star in its previous life as a star, because all stars have winds, therefore they expel material, and the interstellar environment of the explosion is sometimes very thick, for the collapsar model in particular. So basically what happens is, as the ejecta move, they take away material, and they reach a point where they cool enough and they lose their momentum and their energy. And basically what happens is they cool down and we lose them. We don't see them anymore. However, we do observe at that time, we can observe and calculate or measure. We observe the electromagnetic spectrum, the photons. We observe cosmic rays, and we have not observed neutrinos. We could observe neutrinos. And actually, it's not even certain that cosmic rays come from gamma ray bursts or supernova remnants. This is what we could observe if they were there. But we can, from the electromagnetic spectrum alone, we can calculate, in many cases, the explosion energetics, the composition of the jet, and the acceleration mechanisms and the emission mechanisms. So the afterglow, which is in all wavelengths, except for gamma rays, is basically where we get a lot of information. There's a whole industry of afterglow observers. In the actual gamma rays, in the process of producing a merger, we can measure gravitational waves. And if we measure gravitational waves, we can measure the mass of the progenitor or the progenitor nature. That's very important. It's really a huge discovery should it happen. Last but not least, we can do cosmology with gamma ray bursts. We can look back in time by measuring the farthest out gamma ray burst and find out when were the very first stars created. When did the universe started lighting up? It's called what we call it reionization era, after the dark ages of the universe. And we have gone as far back as about 0.3 gigayears in the past, looking back as far as possible. So we hope that with the James Webb Space Telescope, we'll be able to measure even farther back and measure when the first stars were created. So there are now the cosmological probes of the universe, but they could be the farthest cosmological probes in our universe. And we still, that's job assurance, open questions, have open questions. What is the nature of the central engine? We still don't know. How long does the engine last? And how would we know it is a merger if we don't observe gravitational waves? That's a question that certainly is still open. Next serendipity that happened was the same instrument we used to measure gamma ray bursts detected in 1986, I think. Yeah, 6 and then 7. Basically, X-ray bursts that were coming from the same direction of the sky, which means the source was repeating, and they had less energy per burst than a gamma ray burst. So the question that came up didn't rise up to the great debate level because we solved this one fast in the next 10 years. After 3 sources were discovered, it became obvious that this is a different phenomenon. If you remember, I said that gamma ray bursts are a catastrophic phenomenon. Once you kill the star, you can't have repeated bursts. Well, this is a different type of phenomenon, and it's associated with neutron stars and not a black hole. So today, we have several gamma ray burst models associating magnetars, or actually, I jump ahead here, this phenomenon that I'm going to describe in a minute or so with gamma ray bursts. So it looks like everything could be connected together. So a neutron star is a star which has a very dense core. Practically, it's a huge nucleus with neutrons. Basically, all the electrons and the protons are connected, are joined, and they form a neutron. And we have extremely high densities in the middle. And then there is, at the crust, there is some nuclei with electrons. But the result is a very compact star with a radius of about 10 kilometers and an extremely high density. If you weigh a paperclip and Mount Everest, and the paperclip has to be made out of neutron star material, of course, guess who's winning? The paperclip. The size of a neutron star is extremely small. It's a radius of 10 kilometers. So if you were to put a neutron star on the island of Abu Dhabi, it will actually enclose the whole area here, and you can center it wherever you want. I chose to center it here. But this gives you the area that a neutron star, should it fall on this region, I hope nowhere near, and nowhere near Earth for that matter, it would occupy that much of a space. It's not a lot. And it has the mass in it of at least 1.4, 1.8 solar masses. Now, neutron stars were well known as pulsars. Pulsars are neutron stars that have magnetic fields and emit radiation along the magnetic poles. Basically, magnetic fields act as conveyor belts of energy, moving energy away, and they also rotate. So they rotate, neutron stars rotate, and they have magnetic fields accelerating particles away from the poles. Note that all pulsars are neutron stars, but not all neutron stars are pulsars, and I'm saying that because I'm going to go into magnetars, which we believe is an offshoot of the so-called pulsars, which is basically 10% of neutron stars created are magnetars and 90% are normal pulsars. But that definition and that distinction is becoming fuzzier and fuzzier as the time passes. Pulsars have beams that actually, because they rotate, actually pulsars do not pulse, they rotate. This is something I need to clarify. They have a beam. I don't know why they call them pulsars. That's probably because at the beginning they thought they pulsated. But what they do is they rotate, the beam rotates. If the beam is in your field of view, probably you will see it. If it's rotating this way, you will never know there is a pulsar where I'm standing. So think about it the same way as you think about a lighthouse. The beam has to go on the surface of the sea so that the ships will see it. If the beam is completely out of is completely awry and it rotates this way, you'll never see it. And that would be much worse than not seeing a pulsar. Magnetars are neutron stars that were created, and during the creation, they were rotating very fast. They had a very high rotation, a spin, as we say, and also they had a lot of convection. Convection is the phenomenon that you observe when you boil water. The bubbles come up because the material, the hot material rises and the cool material falls. So in that, energy is transferred, and the method that is done is called convection. If there is a lot of convection and there is a lot of rotation, a fast rotation, I should say, then we create what we call the alpha omega dynamo, which is basically a magnetic dipole that is very high depending on the combination of these two parameters. And we then create what we call a magnetar. So magnetars are slowly rotating, magnetically powered neutron stars with extreme magnetic fields. They also are persistent X-ray sources, and they also are actively emitting X-ray bursts, but completely randomly distributed in time. I've been working on magnetars since their discovery, and I would never be able to tell you when one will become active. There is no predictability in their behavior. The difference between the two offshoots, the pulsars and the magnetars, is attributed to the source of their energy. The magnetars produce much more energy in less time. So basically what happens is in about 0 to 10 seconds with birth, things are not very different. But 10,000 years later, the magnetars have lost a lot of energy, and above 10,000 years, they are almost not observable anymore. They have cooled down, so we lose them. There is millions and millions of magnetars, dead magnetars around in the universe. However, pulsars can live up to millions of years. So there is a big difference in their lifetimes. And here is a list of objects with their magnetic fields. And I put the magnetars here to show that they're indeed very, very highly magnetic, and they take the cake. So if you have galactic nuclei, so galaxies, basically, they don't have a lot of high magnetic field. This is the unit. So the unit is about 1% of that. Our galaxy has a millionth of a Gauss, and the planets have higher than the whole galaxy. The sun on the area, on the general field, on the surface is 5 Gauss. The sunspots, the solar sunspots, are where the highest magnetic fields are concentrated. The refrigerator magnet has a higher magnetic, more magnetized than the photosphere. And the common MRI field, the magnetic resonance imaging instrument, has 10,000 Gauss. The strongest sustained laboratory fields are almost 1 million Gauss, and the strongest man-made magnetic field, not actually it didn't last very long. They made it and it died immediately, is 10 million Gauss. Radio pulsars start at 10 to the 12, and there is a fuzzy distinction these days between where this stops and where this ends, but the end product of magnetars, as I will show you soon, goes up to 10 to the 15 Gauss. So they have been measured with the highest magnetic fields. Magnetars have 2 stages, life states, I should say. They're either quiet and sometimes unobservable because their luminosity is very low, and they're active. When they're active, they emit hundreds, thousands bursts. They emit rarely giant flares, and they actually have not been observed to emit any bursts. So the Magnetar movie basically shows what a very simple, again, artist's concept of how magnetars work. There is a neutron star that's rotating, it emits bursts, and all of a sudden it decides to emit a giant flare which affects the magnetic field lines. These are a schematic of magnetic field lines around the star. And it could even reorganize the magnetic field lines and create different combinations of magnetic field of polarity. When that happens, when a magnetar becomes active, we actually see it with the transient monitors that we have, because this is in X-rays. So here is where this magnetar that was discovered in 2013 should have been in 2008. We had images of the area. There's nothing there. 2013, this is the galactic center. It rivals the galactic center luminosity. So it really makes a difference when a magnetar goes bright. In this particular case, we see light echoes from a magnetar. So the magnetar became active. It emitted a lot of photons. These photons passed clouds that are between us and the source, and they created light echoes and rings, as we call them. So in the end, in about, I think it was 4 or 5 days, 5 days here, yeah, there were rings of echoes through the clouds that were lit up with very high energy photons emitted from the magnetar. So the bursts are different. The giant flares, only 3 were detected in 40 years. The workhorse of the magnetars are the short bursts, which last 100 to 250 milliseconds, and thousands have been detected. They look short, like we talked about gamma ray bursts. These are less than 100 milliseconds. This one here is about 20 milliseconds. This one has a precursor, and this one has multiple peaks, and this one is actually longer. It's 400 milliseconds and very bright. There's all kinds as well. And this one is a giant flare that was detected in December 2004, I believe. And this is not what it looked like. The instrument was looking at the different direction when it was first detected. But then, when it got the information that there is a transient and turn around and look at the transient direction, it had to point. And that's why it created the dinosaur basically back here. And actually, my colleague and friend, Yossi Gelfand, was the one who pointed the VLA, the Very Large Array, when the magnetar, which is supposed to be this short, erupted, and radiation hit everything that was our way, because it's emitted in a homogeneous way. It hit first all the satellites that were orbiting around Earth. All of them froze, because there's a command in every satellite that when the flux exceeds a certain level, you stop it, you turn it off so that it doesn't burn. And this is the Very Large Array that Yossi worked on, and he actually detected this explosion as it expanded in time and published, I don't know how many papers by now, several. I think we still monitor it, right, Yossi? Yeah, I know. So where are magnetars? Magnetars are mostly detected, 28 out of 30, in our galaxy, and 2 in the Magellanic Clouds. So this is where we are. This is a model of our galaxy, and these are directions of magnetars, because we don't know their distances in all of them very well. So we know their directions. There are a lot detected from this part of the sky, and this is the anti-center, this is the galactic center. In the anti-center, we have found about 4, but the rest of them are detected in the other way, in the other direction. So basically, what I wanted to tell you with this slide is, we know that magnetars have very high magnetic fields, but how high are they? Ideal efficiency of a rotating and highly convecting neutron star can generate up to 10 to the 16 Gauss. However, the magnetic energy has to be less than the gravitational binding energy. If it becomes more, the star will break out. So alone from these considerations and for the nominal values of property of mass and radius for the neutron star, basically we know that we cannot go higher than 10 to the 18 Gauss. That's the maximum magnetic field we can produce. Now, I'd like to show you a measurement from this particular star that showed the rings. In one day, this is time and this is different count rates. We counted up to 600 bursts. Every line and ones that you cannot see in here is a burst. And my colleague Yuki Kaneko basically saw that there was a kind of a bump here, and when she zoomed in, she realized that yes, there was a bump. So she tried to fit the bump, removing the bursts and just taking the actual energy, the photons that were measured during this period. And when she used one single mathematical function to fit the bump, basically she realized that it wasn't enough. There was a second component that was fit very well with a physical model, which we call the black body. So the necessity of this black body was actually shown with the fit. And the beauty of it is that we can calculate, if we know this is a black body radiation, and because we knew the distance for this source and the temperature of the black body, we could calculate the surface of the area on the surface of the neutron star that was emitting that radiation. And we found out that the radius here is 120 meters. We were able to measure from Earth an area with a radius of 120 meters in a neutron star, which was light years away from us. I don't know that we have another measurement like that. And the basic Rosetta Stone, if I can say this, of pulsars is what we call the breaking versus period diagram. In other words, how do these periods distribute, or how do the pulsars distribute in period and spin down? Spin down is how fast it breaks. In other words, how fast it slows down. And the only reason I'm showing it to you is because magnetars occupy this, predominantly this space, which is the space magnetic field increases this way and age increases this way. So this is the youngest, the highest magnetic fields, the extremes in age and the magnetic field, and the highest periods. And these are other pulsar populations. So, but there are two that are outliers and maybe links with the other populations. And that's the important notion here. Open questions in the magnetars. What is the population of magnetars? We don't know that. What is the link between magnetars and other neutron star populations and other phenomena? Completely open. Other mysteries in nature, which are new, completely new. There was a transient found in very low frequency radio waves that has not been identified. So this is before and after, and this is when the transient was found. This is a new type of transient. We have no idea what it is. We have not been able to identify anything that was active at that time, and this is still fresh. So basically, we'll find out later. Fast radio bursts, there's colleagues here working on fast radio bursts. That's another mystery. We know the durations are milliseconds, their origin is extragalactic, the luminosities are orders of magnitude higher than any short radio transient, and their nature is unknown. For me, it's gamma ray bursts all over again. That is a different, now we found a repeating fast radio burst, which maybe indicates there's two types, maybe indicates that they all repeat, but we don't know. Nothing. In our field, we have, I guess in every field, we have challenges, solutions, and requirements. In astronomy, we have to solve the problem, the challenge of obscurity. In other words, we have to see deep. We use X-rays, hard X-rays for that, or infrared as well. For cosmology, we need to see far, so we need a higher collecting area, infrared, cosmic rays, to use all these messengers and the gravitational waves to be able to beat the challenge of cosmology. We need a lot of space in order to count many phenomena. So we need to see wide. We need all sky instruments. Transients need to be determined by often visiting and revisiting the same place. Confusion, seeing clearly, we need to have instruments that can distinguish between objects which are very close together. We also need to see in all wavelengths, if there is something emitting in all wavelengths, we need to combine all these wavelengths. And in astrophysics in general, we need complementary missions. And this is the mission I will describe in the next couple of slides here, last couple of slides, I should say, which is based on taking advantage of the newly opened window of gravitational waves. This is a discovery. There is an in-spiral of 2 black holes, and this is the gravitational wave that was actually detected. And they did get a lot of publicity. We are proposing to build the Transient Astronomy Observatory, which would be 30 times higher sensitivity for transient studies of black holes, neutron stars, and gamma ray bursts. And it will have synergies with the James Webb Space Telescope, to be launched in 2018, the Fermi Observatory, ground-based telescopes, and the gravitational wave detector that is on Earth, ground-based. That would have a gamma ray transient monitor and a wide field imager. And what it will do is it will try to, so this is what the gravitational wave observatories will pinpoint the source of the gravitational wave detection in the sky. And this is where the field of the actual instrument on the ISS, the International Space Station, will be able to look at. So we can raster this area depending on how big the size is in 1 or 2 or 3 tiles at most. We expect to detect 2 per year, neutron star, and about 12 per year, neutron star black holes. We will, if we do detect that, we will be able to put the astrophysical context into the gravitational waves. We will know what object created them. And as Carl Sagan said, somewhere something incredible is waiting to be known. Thank you.